I'm very excited to be here. In September, Alex and I decided to write this short manifesto. It's called Quantum Punks. I don't know if you had a chance to read it, but we were trying to say, how can we see the developments that we're seeing in the cryptography industry, thanks to maybe blockchain, but more broad applications on the web, and how can we see that in the quantum cryptography world? And we didn't think that we would be organizing like events with everyone from the community. So it's very exciting for me to be here in front of all of you, and that we have a great lineup of speakers that can dive into practical applications. Alrighty, so my name is Nicola, and as Alex mentioned, I worked at Protocol Labs to try to productionize some cryptography that is widely used in decentralized web applications or peer-to-peer applications, and also now more broadly blockchain applications. The talk is divided in two parts. The part one is the quantum punk thesis, which is a cypherpunk application, so applications beyond defense use of QKD. So cypherpunk applications, applications that can empower the users to, well, we're gonna go into that in a second. So cypherpunk applications of quantum cryptography can accelerate the quantum industry. New applications in quantum cryptography can accelerate the quantum industry. And part two is maybe a short path to a new wave of quantum applications. And by new wave, I really mean beyond QKD. Now, big disclaimer, I don't come from the quantum industry. I know very little about the quantum industry. I don't come from quantum cryptography. I'm still learning with some of you. I come from cryptography, and I come from industry cryptography. And I want to bring this intuition and understanding to the community. And so if I make mistakes or I say something that is wrong, please be nice. So when I joined Protocol Labs 8 years ago, we were looking into a niche field of research which was called zero-knowledge proofs. And I want to talk about this because I want to show what happened once we found product market fit for zero-knowledge proofs in the cryptocurrency industry. And I wish a very similar journey for quantum cryptography applications. So in the 80s, there were theoretical constructions. Then we had first papers that said, maybe zero-knowledge. Are you familiar with zero-knowledge proofs? I'm just going to say, OK, good. I'm assuming this. So in 2013, we had a first practical paper, and people in the researchers in this industry started to look into practical applications. And one practical application was Zcash. So at the very beginning, verifiable computation, or more broadly, zero-knowledge proofs, were designed to have a very powerful server would generate a proof of a computation to some very light client. It turned out that Zcash used it in the opposite way. A very powerful client wanted to generate a proof for a very light server, and this light server is the blockchain. So Zcash used zero-knowledge proofs to have confidential transactions. And what happened is that Zcash put quite a lot of effort in research and development to make these proofs even more practical than what happened in the paper. And after that, there's been an explosion of more zero-knowledge proofs. Filecoin was a product of Protocol Labs. They used zero-knowledge proofs for generating a small proof of space. You had Mina, which is another confidential transaction. And well, you have Aztec, Mina, Helio, which I put this into the broad category of confidential transactions. And then you have other technologies that zero-knowledge proofs have been used for scaling blockchains with ZK, rollups, and layer 2s. And every other year, there is a new narrative for zero-knowledge proofs. What I'm trying to say is once zero-knowledge proofs found a product market fit application in the cryptocurrency industry, a lot of money, some speculative money and some not, have been poured into the industry. And we had, this meant that not only you had some companies doing these things, but these companies needed new primitives, and so they went and started to fund more research, and they funded research centers, they fund conferences, and professor grants, and in a way, the cryptocurrency industry, you need to think of it as a client of a $3 trillion market cap. And just last quarter of 2023, we had several hundreds of millions of dollars invested in zero knowledge proofs company, which is like a very small niche of the much broader cryptocurrency industry. But this didn't just mean we have new companies that work on better software. We even had companies that work on better hardware. There are, I think there are like quite a few zero knowledge proofs acceleration hardware companies. And so this is to say, and also we had prizes for winning, more broad industry prizes for academia for trying to improve these systems. And this is to say that if we do find a small application like Zcash did in the early days, I would say in general, but specifically in the cryptocurrency industry, then you would have this, I think that we will have this very similar effect of impact and funding and advancement in research. And so this is one of the theses of what we're saying with the quantum punks, is that cypherpunk gave us, the cypherpunk movement gave us great new tools like encryption, signatures, that eventually led to what is the e-commerce, the web and social media and blockchains and maybe more. But ultimately, we think that there is a limit to what you can do with classical cryptography, and then maybe there's a broader set of cypherpunk applications in the thanks to quantum cryptography. And so, for example, the cypherpunk movement in the 80s said, we don't want to trust the bank institution. We want to make sure that the bank is run by a set of anonymous nodes in a network, and that's how eventually we came up with blockchains. But can we do better than this? And I think even before, so can we avoid going through a ledger, use a ledger in first place? And even before Satoshi Nakamoto, you have this idea, which unfortunately is not practical. And this is like the quantum money application. And we're gonna cover that later on. But the idea is, if you have quantum properties, then you don't need to tell to a third-party ledger which transaction has gone first, because the moment you send quantum money to your counterparty, you could not have sent this money to two different people. So what's in there in quantum cryptography today for those that are not familiar with this? So first of all, quantum is just as a word is like a large category of things. It's almost like when we say quantum, most people think of quantum computing, but we do have quantum sensing, quantum memory, quantum internet, randomness, many applications. And similarly in crypto, when we say crypto, most people think about cryptocurrency. Or at least in the cryptography industry, we don't think about cryptocurrency. But people think about encryption, blockchain, FHE, MPC, and so on. But is there something in the intersection? And the intersection is very small. I think maybe an indicator is QCrypt accounts for 300 people that go to the conference, and maybe not all of them just do quantum cryptography. And this is just the academic world. So we do think that the intersection is small, and mostly because I would say, broadly speaking, most people in the quantum industry focus on quantum computing, and a lot of people in the crypto industry, due to where the money is focusing on blockchain. And the quantum crowd thinks that cryptocurrency is just speculation, and the crypto crowd thinks that quantum is very years away. So there is also this like social problem that the two communities don't really speak to each other, and so that's what Alex and I saw, which is like there is an opportunity to bridge the gap and see what's in the middle. And so what is in the middle? And so we try to look deeper, and we find mostly QKD. And but is there something beyond QKD? And even if you look at the quantum cryptography industry, most of the companies that work on the quantum cryptography either work on QKD or work on post-quantum cryptography. And these are and for specifically to this talk, I'm mostly interested on applications beyond QKD and not applications that are post-quantum cryptography. I really mean, what are the applications that use quantum properties? And so there is more than companies that just do QKD, but there are very few. But ideally, in the future, we see this intersection to grow because hopefully we solve some hard problems. But there is, at least the literature tells us that there is more. There's applications of copy protection, certified deletion, position verification, unclonable encryption, and this more broadly quantum money. But there is also other application that people in the room today will talk about, which is very secure cloud or one-time programs and more. And this is like a pure use of quantum, but there is also quantum-inspired applications, and so maybe this intersection is much bigger. And the whole thesis about this quantum punk movement is to create this intersection and make it bigger, and trying to accelerate this ideally by jointly having industry and academia from both sides of this Venn diagram to go and talk to each other and trying to understand what are important problems to solve. And so this is what the quantum punk is about. Like, let's use quantum technology and let's build applications that are secured by physics. And the thesis is that we're going to have, on one hand, new applications, and on the other hand, new applications will accelerate development of new research, not just in quantum cryptography, but also new quantum technologies. If we have applications that would pay for quantum memory, then we would have maybe more funding in quantum memory. So there is many things have happened in the past 6 months. I just want to zoom down in a maybe myopic way of what happened out of this crowd since our last event. So there are actually new companies that spawn up with this quantum punk DNA. And some were already there, for example, VeryCloud. Well, we have some others, like Nicola, that is building, well, they're going to speak about it. We have Shift, and these are on the category of what we call cryptophysics, like actually using quantum properties. And then there is also another category, which we're not dismissing, which is the category of post-quantum cryptography, but used with more, say, cypherpunk applications. And then we will have Tectonic and Project 11 that will mention what they're working on. But more broadly in the industry, Quantinuum had this first example of quantum tokens over fiber networks. IDQuantic got acquired by IonQ, and so there are things happening. Ideally, next time we speak, that map becomes a much bigger map. So, summary of this first part of the talk: we believe that new applications, not just cryptocurrency applications. So I think that's myopic to think in that way, but new applications, like either driven by cryptocurrency or new cypherpunk applications, will lead to new cryptography, which make the intersection bigger, and really they expand what we can do, both with hardware and software. I'm going to touch now into the second part, which is what are the things that Alex and I have seen in the past few months that we think there might be some opportunity. And the talk is going to go in this line, which is first we're going to have what we think is practical is to do applications that use no memory because we don't have memory, and that ideally we can deploy on live networks, and then we're going to talk about something more far in the future, which is the verifiable quantum cloud. So what can we do today? So unfortunately, we are limited by the constraints of the hardware, and so to give you an example. We cannot use a lot of quantum compute because we don't have quantum computers that have a lot of qubits to do all the nice things that we would like to do. We would like to have more memory so that we can have better networks, but also applications that require memory. Ideally, if we have better memory, we could get closer to these. We could make applications like quantum money more realistic. And then finally, most applications only work under short distance because we have most of the quantum networks have, especially fiber optics networks, have this limit of 100 kilometer range. And the reality is that today, this triangle, the range of operation that we have is very small. Like I said, we have little no compute, little no memory, and very short distance. And the problem is that I gave this presentation the other time, and the professor Orsatat said, "Oh well, this triangle is not like this; it's more squashed." And I asked, "What do you mean it's squashed?" Is that some of these parts on the triangle don't really interact well with each other. So maybe you have memory, but you cannot connect them to the communication hardware. Maybe you have communication hardware that you cannot connect to compute. So it's the range of opportunities. It's very small, and it's mostly due to the constraint of the hardware. And ideally, we grow this triangle, and through time, this triangle will grow. But there is a chicken and egg problem, which is I do believe that. I mean, unfortunately, we don't have beyond. I think quantum computing is driving a lot of the research and development of a lot of those components. But even of quantum computing today, there is no real applications that can. There's no applications for which people would buy a quantum computer today. Hopefully, this is going to change. Or hopefully, I'm wrong. But one of the things that Alex and I are trying to push is that maybe there are applications that fit in the triangle that are practical today that you can do with quantum cryptography. And QKD is one of them. It's just that it's a niche application, and maybe we have more broad usage of quantum communication based cryptography that don't require memory, it doesn't require compute. So it is a chicken and egg problem. Until we find an application, we cannot increase the size of the triangle. The size of the triangle doesn't increase because there is no demand for applications. So what can we do today with the quantum cryptography? Well, as I mentioned, QKD is one. There might be other applications. I'm aware of a few. I'm aware, we're scrolling through the literature and trying to understand what are the things that we could do with today's hardware. And for example, we are very interested about this idea, which is called tokens for Mac. And the idea is that someone can mint a quantum token that can be sent around and eventually measured to generate a Mac. And this means that you can have you can use this as giving to someone else the capability to do something. And you can build private quantum money on top of this. But there is maybe more applications. Some in the crowd are looking into applications of where you can run fair exchange, or maybe proof of work, or maybe combining quantum with trusted hardware to get one-time programs, and so on. And so the main point here is that the quantum tokens for Mac it is a no-memory application. So ideally, you have a quantum tokens minter that sends the token to someone, then they send it to someone else, then they send it to someone else, they eventually send it back to the minter. And then if someone needs this new token, the minter will create a new token. If we had memory, this token could just sit on memory, but we don't have memory. So what I'm trying to say is that the only applications that we can have today are those that the quantum state is sent around and sent back, or sent around and measured. I think this is a sketch. We're going to look into this later, but maybe there are ways to connect applications of the blockchain world to the private quantum money applications. Maybe you have, in high level, the idea is that someone locks money on a blockchain and instruct a private quantum money network to move the money around, and then they ask some sort of like a minter, which could be a single node or an MPC, to look at the blockchain, mint the token, they spend the token around, and then eventually send the token back. So we're going to look into this later, so hopefully this doesn't confuse people. But the idea is, I wonder if there are applications that go, that really cross between the two worlds. The last item that I want to talk about is this verifiable quantum cloud. So let's say that we want to, it's this developer networks. So assume that we do have an applications of private quantum money or quantum tokens for Mac or similar applications. Now, we don't just want to have these applications. We want to run them in live networks. And so Alex and I said, let's implement, not working? Okay, good. Great. Let's assume we go and implement in practice this quantum tokens for Mac application. And then if we were to do that, where are we going to deploy it? And there are small local networks around, some in someone's lab, some are more broader city networks. And the idea is that, that's where we are now, the idea is that eventually we're gonna have like a globally connected world where there is a quantum communicating device everywhere. But that is far in the future. And so we must focus on small local networks. But the problem with these small local networks is most of those only implement QKD protocols. And this is problematic because if you want to do protocols that are not just QKD, but passing quantum state around without it being measured, having some routing of some quantum state across multiple devices, there are a few networks that are like this. There is a few entanglement-based networks, but most of the networks that we talk to, they only offer QKD networks. And not only, those, so I should have done a diagram, which is a the big circle is all the people that do QKD network, like all the networks. Then if you remove QKD, you have a very small set. And in this small set, we asked to some of these providers, can we test our applications in your can we deploy our application in your test networks? And it turns out that there's not developer-friendly way to except simulators. There's no developer-friendly way to deploy these applications. There is no, there are some production networks, but very few are easy to access. And if we don't have developer networks, it will be impossible to have hackers, people that want to experiment, to play with these networks. And most importantly, most of these networks are very custom solutions and require several months to set up. So my dream here is that eventually there will be a platform where there are multiple networks hosted in someone's labs, like TableNets, or hosted in some cities, that you don't just have to call the company and the company would tell you, well, maybe you can rent, maybe the node can give you, maybe the university can give you a node for some period of time. Ideally, we should have like a cloud-like experience for people that want to deploy this kind of applications. Otherwise, people don't even start looking into, should we build applications? Because there is no live network to test your stuff. So ideally, we do have a quantum network discovery platform where you can see some networks around, and some labs can rent their table computers connected with each other, which we call these table nets. And ideally, you rent a node to play with it. So let's move on. So we had no memory applications that ideally we deploy on these developer networks that are easy to deploy. And then I want to talk about one last item, which is maybe all I talked about until now. It could be practical. Like we can implement things like quantum tokens for Mac. Maybe there's more applications. And we could even deploy them on live systems. It's just a coordination issue of like connecting the right people together to to deploy these applications. And then, but assume that you go through this whole effort of coming up with an application, deploy it in a test network, then you want to make sure that it could be widely used across the globe by anyone, even if they are not quantum enabled. And how are we going to get there? And the status quo is that we're going to have small networks now, and then we're going to have a large network in the future. But is there like an intermediate step? And the intermediate step is that you do connect to these local networks, and by running a node in this network. But this is not going to scale. So you need to go through, for example, trusting a node in that network. But the moment you trust a node, you don't need most of these quantum properties, because there are better solutions. But ideally, what you do verifiable delegation of some computation or some state measurement to some of these nodes in this local network. And so finally, instead of waiting for the fully connected world, you can have many small table nets or like small city networks that you can connect to classically by doing verifiable delegated instruction. And for those that are expert in the field, there are like verifiable quantum computing more broadly, but specifically for the kind of protocols that we care that don't require computing, we do want to have better solutions to problem like remote state preparation and remote state measurement, because this gives the ability to a classical client, so anyone that has a mobile phone, to connect to these networks, do quantum operations or quantum communication protocols, based cryptographic protocols, and being able to use these applications in the real world. Spoiler alert, the remote state preparation is not practical, but maybe like we did in cryptography, even zero knowledge proofs back in the day were not practical, and people started to say, maybe we can add wonky new assumptions, or maybe we can add MPC, or maybe we can add a trusted setup. So I wonder if there are like alternative ways to look into remote state preparation to make it more practical. I don't know. And so just to summarize part 2, we do think that we should look for no-memory applications that ideally we can deploy in developer networks which currently don't exist. And eventually, these become larger networks, not just because the network, not just because we have a global network where everyone has quantum-enabled devices, but where also classical-enabled device can talk to the rest of the network through verifiable delegation. And again, this is a summary of the talk, and I just want to say one thing is the reason why we're having this event is for people like me, and they come from an industry to try to, my goal personally is to try to understand what of these things can we make practical so that we can deploy real life applications. And I guess on the other side, for example, from academic quantum, cryptography is like finding out what problems would be important to solve. So talk to one another, source each other's problems, and thanks a lot. Okay, maybe we have a couple of questions. Or observations, like I'm open to feedback as well.
So at least this last part, it's hard to see how to do it without quantum computing, right? So at some point I think 384 states won't be sufficient, right?
I agree. So, but
yeah, because it depends on what they want to verify. If the size of the computation they want to do on the server is small, it can be done on the current thing. So easy for the using quantum communication. I think you're using about the classical communication.
I understood that he wants to do it in your cell phone.
Okay.
so
I
no,
agree.
so hold on. I said before, up until this point here, whatever, up until developer network, I agree. But all this verifiable quantum cloud, big spoiler alert, is not practical. It's like my wish to start to look at this problem with alternative ways, because maybe we don't need to. In the cryptography industry, in the quantum, for cryptocurrency application, we really looked into the wonkiest assumptions. And we started to look into trusted setups, MPC, algebraic group models, and we started to see at really alternative stuff to make things practical, or non-falsifiable assumptions. And so I wonder if there are alternative ways to look into this problem, then maybe it could be done with the simpler
Use quantum communication.
Ideally using quantum communication, yeah. Yeah, so, I mean, my pitch, for the expert in the room, my pitch here is that let's increase the space of quantum communication-based quantum cryptography applications. Because that's the only thing that we have practical. And if we want to deploy things in the real world in the next 1 to 2 years. Anything else, unfortunately, is too hard to do.
All right. Thank you, Nico.